Welcome. In this session, we'll explore an interesting problem: minimize product sum of two arrays. We'll dive into the logic and strategies to pair elements from two arrays to achieve the minimum product sum. Let's get started. In this problem, we are tasked with minimizing the product sum of two arrays, nums1 and nums2, both of size n. The product sum is calculated as the sum of the products of corresponding elements from the two arrays, specifically, nums1, I, asterisk nums2, I, for all indices I from 0 to n1. The twist here is that while the elements of nums2 must remain in their original order, we are allowed to rearrange the elements of nums1. The goal is to determine the smallest possible product sum after rearranging nums1. For the input, we are given two lists of non-negative integers, while the output will be a single integer representing the minimum product sum achievable. Let's look at an example. Suppose nums1 is 5, 3, 4, 2, and nums2 is 4, 2, 2, 5. To minimize the product sum, we can rearrange nums1 to 2, 3, 4, 5. By calculating the product sum, we get 2 asterisk 5 plus 3 asterisk 4 plus 4 asterisk 2 plus 5 by 2, which equals 40. This is the smallest possible product sum for these inputs. In another example, if nums1 is 1, 2, 3, 4, and nums2 is 1, 2, 3, 4, the optimal arrangement of nums1 would be 4, 3, 2, 1. The product sum then becomes 4 asterisk 1 plus 3 asterisk 2 plus 2 asterisk 3 plus 1 by 4, which equals 20. By carefully rearranging the elements of nums1, we achieve the minimum product sum. Now consider another example where nums1 is 1, 8, 3, 5, and nums2 is 2, 3, 7, 8. Rearranging nums1 to 8, 5, 3, 1 minimizes the product sum. Calculating this, we find 8 asterisk 2 plus 5 asterisk 3 plus 3 asterisk 7 plus 1 by 8, which equals 86. This rearrangement ensures the smallest possible product sum. The problem also comes with constraints to guide our solution. Specifically, both arrays will always have the same length n, where n can range from 1 to 100,000. All elements in the arrays are non-negative integers, and their values can go up to 100. These constraints ensure that the solution must be efficient and scalable for larger inputs. To further clarify, let's explore a few edge cases. For the smallest possible input size, where both arrays contain a single element of 0, such as nums1 equals 0 and nums2 equals 0, the product sum is simply 0 asterisk 0 equals 0. For identical arrays, like nums1 equals 1, 2, 3, and nums2 equals 1, 2, 3, rearranging nums1 in descending order minimizes the product sum. Finally, if one array contains only zeros, for example, nums1 equals 0, 0, 0, and nums2 equals 5, 5, 5, the product sum will always be 0, regardless of how we rearrange nums1. These examples demonstrate the variety of scenarios we need to consider when solving the problem. To solve the problem of minimizing the product sum of two arrays, we start by recognizing that how we pair the elements of nums1 and nums2 directly impacts the result. The goal is to minimize the sum of nums1, I, asterisk nums2, I, across all indices. One way to approach this is through a brute force method. The intuition here is simple: by trying all possible permutations of nums2, we can calculate the product sum for each pairing with nums1 and choose the smallest value. To implement this, we would generate all permutations of nums2, which can be done using a library function, and compute the product sum for each permutation. However, the drawback of this approach lies in its computational complexity. Generating all permutations of nums2 requires factorial time, specifically O(n), and for each permutation, calculating the product sum adds another O(n). This results in an overall complexity of O(n), *n), which is highly impractical for larger input sizes. Additionally, this approach does not take advantage of any mathematical properties that could simplify the problem, making it inefficient and unsuitable for real-world use cases with larger arrays. A more efficient approach involves leveraging sorting to minimize the product sum. The idea is to pair the largest elements in one array with the smallest elements in the other array, reducing their overall contribution to the sum. To achieve this, we can sort one array in ascending order and the other in descending order. Specifically, we sort nums1 in ascending order and nums2 in descending order. Then, we compute the product sum by iterating through the paired elements and summing up their products. The implementation is straightforward. Sorting both arrays takes O, n log n, and calculating the product sum is an O, n operation, resulting in an overall time complexity of O, n log n. This optimized approach not only reduces the computational cost compared to the brute force method but also guarantees the minimum product sum by leveraging the mathematical properties of the problem. However, it does require sorting the input arrays, which may not be ideal in scenarios where the input must remain unsorted. Nonetheless, the advantages of efficiency and simplicity make this method a strong candidate for solving the problem. The strategy we chose for this problem is the optimized approach using sorting. This decision was based on several factors. First, the brute force method, while exhaustive, is computationally expensive and becomes impractical as the size of the arrays increases. Sorting and then pairing elements based on their relative sizes, on the other hand, is mathematically sound and efficiently minimizes the product sum. With a time complexity of O, n log n, this approach is well suited to the problem's constraints and scales effectively with larger inputs. The key insight here is recognizing that the product sum is minimized by pairing the largest elements of one array with the smallest elements of the other. This eliminates the need for exhaustive searching and provides a direct path to the optimal solution. While we considered the trade-offs, such as the requirement to sort the arrays, the benefits of efficiency and guaranteed results far outweigh the downsides. Compared to brute force, which is computationally prohibitive, and other potential methods that lack the rigor of sorting, the chosen strategy is clear and effective. The optimized sorting approach offers the perfect balance of simplicity and efficiency, making it ideal for solving this problem. With a time complexity of O, n log n, it is scalable and capable of handling larger input sizes comfortably. By directly using sorting to pair elements strategically, this method leverages the mathematical properties of the product sum to guarantee a minimum result. This approach not only avoids the computational pitfalls of brute force but also provides a reliable and elegant solution to the problem. Overall, the combination of efficiency, simplicity, and mathematical soundness makes the optimized sorting approach the most practical and effective strategy. The problem we're solving is to minimize the product sum of two arrays, nums1 and nums2. The product sum is calculated as the sum of nums1, I, asterisk nums2, I, for all indices. To achieve the minimum product sum, we need to strategically pair elements from the two arrays. The optimal approach is a greedy solution where we pair the smallest elements from one array with the largest elements from the other. To implement this, the first step is sorting the arrays. We sort nums1 in ascending order to access its smallest elements first, and nums2 in descending order to access its largest elements first. This sorting step ensures that we can maximize the efficiency of our pairings and adhere to the greedy principle of minimizing the product of each pair. Sorting is a crucial pre-processing step that sets up the rest of the algorithm. Once the arrays are sorted, we calculate the product sum. We initialize a variable, product_sum, to 0. This variable will store the cumulative sum of the pairwise products. Then, we iterate through the indices of the arrays using a loop. For each index I, we multiply the corresponding elements from nums1 and nums2, specifically nums1, I, asterisk nums2, I, and add the result to product_sum. This process ensures that we are incrementally summing the smallest possible contributions from each pair. Once the loop is complete, the value stored in product_sum represents the minimum product sum. This final value is then returned as the result of the algorithm. The effectiveness of this approach is rooted in a few key insights. First, the greedy pairing principle ensures that pairing the smallest element of one array with the largest element of the other minimizes the overall product sum. This is because the product of two numbers is smallest when their values are distributed across the range of the arrays. Second, sorting the arrays is an efficient pre-processing step that allows us to create optimal pairings without additional computation. Sorting takes O, n log n, time, which is significantly faster than the factorial complexity of brute force approaches. Finally, this method avoids the inefficiency of trying all permutations of nums2, which would take O, n, time. By focusing on sorting and a single pass through the arrays, the greedy approach achieves optimal results in a fraction of the time. The algorithm also uses minimal resources, relying only on the input arrays and a single variable for the product sum. Analyzing the algorithm's complexity, the time complexity is O, n log n, due to the sorting of both arrays. The subsequent loop to calculate the product sum adds O, n, making the overall time complexity O, n log n. In terms of space complexity, the algorithm operates in O, 1, additional space if the sorting is done in place. Otherwise, it requires O, n, space to store the sorted arrays. The algorithm also handles several edge cases. If the arrays have unequal lengths, it's important to throw an error or handle this scenario explicitly, as the problem assumes equal lengths. For arrays with negative numbers, the pairing principle still holds, since the smallest and largest elements minimize the product sum regardless of their signs. Zeros in the arrays don't affect the correctness, as multiplying by 0 simply results in 0, which is the minimum contribution possible. To better understand the algorithm, let's go through an example. Suppose the input arrays are nums1 equals 1, 3, 5, and nums2 equals 6, 4, 2. First, we sort nums1 in ascending order, which gives 1, 3, 5. Next, we sort nums2 in descending order, resulting in 6, 4, 2. Now, we pair the elements and calculate their products. 1 asterisk 6 equals 6, 3 asterisk 4 equals 12, and 5 asterisk 2 equals 10. Adding these values together gives a total of 6 plus 12 plus 10 equals 28. Thus, the output of the algorithm is 28, which represents the minimum product sum for these input arrays. This example illustrates how the sorting and pairing process achieves the desired result efficiently and correctly. This solution is designed to minimize the product sum of two arrays, nums1 and nums2. The product sum is defined as the sum of nums1, I, asterisk nums2, I, across all indices I. To achieve the minimum product sum, we need to strategically pair elements of nums1 and nums2 such that smaller elements in one array are paired with larger elements in the other. The first step in the code is to sort nums1 in ascending order, nums1.sort, and nums2 in descending order, nums2.sort, reverse equals true. Sorting in this manner ensures that the smallest elements from nums1 are paired with the largest elements from nums2, leading to the smallest possible products when multiplied. Next, we initialize a variable product underscore sum to 0, which will store the cumulative sum of the products of the paired elements. We then iterate through the indices of nums1, or equivalently nums2, since both arrays have the same length. At each step of the loop, we calculate the product of the corresponding elements of nums1 and nums2 and add it to product underscore sum. This ensures that we are building up the minimized product sum incrementally. Finally, the function returns the value of product underscore sum, which represents the minimized product sum of the two arrays. This approach runs in O, n log n, time complexity due to the sorting operations, and the subsequent loop runs in O, n, making it efficient for large input sizes. The space complexity is O, 1, as no additional data structures are used beyond the input arrays. Here, we start by importing the necessary utilities and defining our class solution with the method minProductSum. The goal of this method is to minimize the product sum of two arrays, nums1 and nums2. To achieve this, the first step is sorting nums1 in ascending order using arrays.sort. Then, nums2 is also sorted, but in descending order. Since Java's sort method only sorts in ascending order, we call a helper method, reverseArray, to reverse the order of nums2 after sorting. This ensures that the smallest elements of nums1 are paired with the largest elements of nums2, which helps minimize the overall product sum. Next, we calculate the product sum by iterating through both arrays, multiplying corresponding elements, and adding the products to a variable, product sum. Finally, the method returns the computed product sum value. The helper method reverseArray is defined below to efficiently reverse nums2. The reverseArray method is a utility function that takes an array as input and reverses its elements in place. It uses a two-pointer approach, where one pointer starts at the beginning of the array, and the other starts at the end. These pointers move toward each other, swapping the elements at their respective positions until they meet in the middle. This ensures the array is fully reversed. Once the reversal is complete, nums2 is sorted in descending order as needed, and this completes the implementation. The overall approach ensures an optimal solution by leveraging sorting and efficient element pairing to minimize the product sum. To solve the problem of minimizing the product sum of two arrays, let's start with our first example where nums1 is 1, 3, 5, and nums2 is 6, 4, 2. Step 1 involves sorting nums1 in ascending order. In this case, nums1 is already sorted, so it remains 1, 3, 5. For step 2, we sort nums2 in descending order. After sorting, nums2 becomes 6, 4, 2. Now, in step 3, we calculate the product sum. We initialize product underscore sum to 0 and iterate through the indices of both arrays. At I equals 0, we add nums1, 0, multiplied by nums2, 0, which is 1 times 6, giving us a product underscore sum of 6. At I equals 1, we add 3 times 4, bringing product underscore sum to 18. Finally, at I equals 2, we add 5 times 2, resulting in a total product underscore sum of 28. The final product underscore sum for this first example is 28, so the output is 28. Now, moving to the second example, nums1 is 4, 1, 2, and nums2 is 5, 3, 3. In step 1, we sort nums1 in ascending order, and it becomes 1, 2, 4. For step 2, nums2 is sorted in descending order, but since it is already in the desired order, it remains 5, 3, 3. In step 3, we initialize product underscore sum to 0, preparing to calculate the sum of products by iterating through the arrays. To calculate the product sum for the second example, we loop through the indices of nums1 and nums2. At I equals 0, we add nums1, 0, multiplied by nums2, 0, which is 1 times 5, resulting in a product underscore sum of 5. At I equals 1, we add 2 times 3, bringing product underscore sum to 11. At I equals 2, we add 4 times 3, resulting in a final product underscore sum of 23. Thus, the output for this example is 23. Now, in the third example, nums1 is 1, 1, 1, 1, and nums2 is also 1, 1, 1, 1. In step 1, sorting nums1 in ascending order keeps it as 1, 1, 1, 1, since it's already sorted. Similarly, in step 2, sorting nums2 in descending order also keeps it as 1, 1, 1, 1. For the third example, step 3 involves calculating the product sum. We initialize product underscore sum to 0 and iterate through the indices of nums1 and nums2. At I equals 0, we add nums1, 0, multiplied by nums2, 0, which is 1 times 1, resulting in a product underscore sum of 1. At I equals 1, we add 1 times 1 again, bringing product underscore sum to 2. At I equals 2, we add 1 times 1 once more, increasing product underscore sum to 3. Finally, at I equals 3, we add 1 times 1, giving us a final product underscore sum of 4. The output for this example is 4, and that concludes the solution walkthrough for this problem. Here, we analyze the time complexity of the solution step by step. First, sorting the array nums1 in ascending order is performed using Python's timsort algorithm, which has a time complexity of O, n log n, for an array of size n. Sorting nums2 in descending order also uses timsort, and since the sorting direction does not affect the algorithm's underlying operations, this step also takes O, n log n, time. Finally, we calculate the product sum by iterating over the elements of the arrays. Each iteration involves a constant time operation of multiplication and addition, and since the iteration runs 4 n elements, this step has a time complexity of O, n. To summarize the time complexity, sorting nums1 takes O, n log n, sorting nums2 also takes O, n log n, and computing the product sum through the loop adds another O, n. Since O, n log n, is the dominant term, the overall time complexity of the solution is O, n log n. Shifting to space complexity, Python's timsort algorithm is considered an in-place sort that generally requires only O1 additional space. However, some implementations may require O, log n, auxiliary space for recursion. The input arrays nums1 and nums2 do not require any extra memory allocation as they are passed directly as arguments. Additionally, we consider the space required for auxiliary variables. The product underscore sum variable, used to store the cumulative sum, and the loop index variable both require constant space, or O1. Combining all of these factors, the total auxiliary space usage is O, log n, for sorting in O1, for other variables. Therefore, the overall space complexity of the solution is O, log n. Comparing this optimized solution to a brute force approach highlights its efficiency. A naive method would involve generating all permutations of nums2, which would take O(n) time, and evaluating the product sum for each permutation, adding another O(n) per permutation. This results in a total time complexity of O(n)(n), which is vastly slower than the O(n) log n complexity achieved by sorting the arrays strategically. The time complexity of this solution is dominated by the sorting operations, and we can validate this mathematically. TimSort sorts an array of length n by dividing it into smaller runs, sorting each run in O(n) time, and merging them over O log n steps. This gives a total time complexity of O(n) O log n or O(n) log n. While the for loop contributes O(n), this is negligible compared to the O(n) log n from sorting. Therefore, the overall time complexity remains O(n) log n. When analyzing best, average, and worst cases, the sorting steps consistently take O(n) log n, regardless of input order, and the for loop always iterates n times. As such, the time complexity remains O(n) log n across all cases. In summary, this optimized solution drastically improves upon the brute force method by reducing the time complexity from O(n) to O(n) log n, making it feasible for large input sizes. The space complexity is also minimized to O log n due to the efficient in-place sorting operations. Together, these improvements make the approach both time efficient and space efficient, achieving the goal of minimizing the product sum in a computationally optimal way. When working on minimizing the product sum of two arrays, there are several common mistakes to be mindful of. First, it's crucial to sort the arrays properly. A common misunderstanding is sorting both arrays in ascending order, but this approach does not always yield the minimum product sum. Instead, the correct strategy is to sort one array in ascending order, while sorting the other in descending order. This ensures that the smallest values in one array are paired with the largest values in the other, which minimizes the product sum. Another mistake to avoid is using a brute force method to generate all permutations of one array and calculate the product sum for each pairing. While this approach might work for small inputs, it becomes computationally infeasible for larger arrays due to the factorial growth in complexity. It's far more efficient to use a sorting-based greedy approach. Lastly, don't overlook edge cases such as arrays containing zeros or negative numbers. These can significantly impact the result, so your solution needs to handle them properly. For example, if one array has negative values, improper sorting could result in a maximized product instead of a minimized one. Another common pitfall is assuming that the two arrays are always of equal length. If the problem involves arrays of different sizes, failing to validate input constraints or handle padding can cause index errors and unexpected behavior. To prevent this, always ensure that your solution accounts for variations in input sizes. Additionally, time complexity is a critical consideration. Sorting the arrays unnecessarily during intermediate steps can lead to inefficiencies, especially if sorting is performed multiple times. Instead, you should aim to sort each array only once. After sorting, a two-pointer technique can efficiently pair elements to calculate the product sum. This approach minimizes redundant operations and keeps the solution optimal. Minimizing the product sum is a classic example of a greedy algorithm problem, and it's often used in interviews to test your ability to recognize and implement greedy strategies. One key aspect to articulate is why sorting works for this problem. Specifically, explain that pairing the smallest element of one array with the largest element of the other minimizes each individual product term, which leads to the smallest overall sum. Interviewers may also expect you to discuss time-space trade-offs. For example, the sorting-based greedy approach has a time complexity of O(n) log n, which is much better than the O(n) complexity of brute force. Be ready to address edge cases as well, such as arrays with zeros, negative numbers, or very large inputs, as these can test the robustness of your solution. Lastly, interviewers may explore variations of the problem, such as maximizing the product sum instead, or solving it without modifying the input arrays by working directly with indices. This type of problem is closely related to several other optimization problems that use greedy algorithms. For example, in LeetCode problem 1353, you aim to maximize the number of events you can attend by scheduling them strategically, which is similar to minimizing the product sum using sorting. Another example is LeetCode problem 1029, two-city scheduling, where you minimize travel costs by carefully pairing values. Similarly, LeetCode problem 1710, maximum units on a truck, requires optimizing the allocation of resources using sorting and greedy allocation. Lastly, LeetCode problem 1833, maximum ice cream bars, involves cumulative sums and sorting to achieve an optimal solution. These problems all share the theme of strategic pairing or allocation, making them great practice for recognizing and applying greedy methods. When approaching this problem, it's important to understand the alternative methods available. The optimal approach is the greedy sorting technique, where you sort one array in ascending order and the other in descending order. This has a time complexity of O(n) log n, due to the sorting step, and a space complexity of O(n) if you store the sorted arrays separately. A less efficient alternative is the brute force method, where you generate all permutations of one array and calculate the product sums. While conceptually simple, this approach has a prohibitive time complexity of O(n) and should be avoided for larger inputs. Another efficient method is the two-pointer technique. After sorting the arrays, you use two pointers to traverse them, one moving forward and the other backward, calculating the product sum as you go. This technique combines the efficiency of sorting with the simplicity of linear traversal, resulting in a time complexity of O(n) log n, and a space complexity of O(1) if sorting is done in place. Great work! In summary, we explored how to minimize the product sum using sorting and pairing strategies. Sorting one array in ascending order and the other in descending order proved to be the optimal approach. Remember, this technique has broad applications in optimization problems. Thanks for joining, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!